That's mainly due that the distribution in the Princeton area is following a normal distribution and that levels itself out. A better way would work with a downscaled temperature scheme and using the temperature. So we have the in the picture on the right, the left, we see the different points that coming from the data set. Underlying is the DEM, and by using the decaying function of temperature over elevation, we could derive a temperature index for each individual cell, instead of, as I used in this study, one value for the whole area. Classifying then the risk, so we again work from the topographical risk to a fuel risk, combining that to a fire risk, and correcting that for drought. And in this case, the Spain dataset was decreased in risk because, as we saw in the previous graph, it has not over the whole area a high risk. For North America, it was not necessary. The drought risk was high enough. The good point here was that I said nothing. Every study area must have at least have 40% drought or 40% fire risk in areas that are prone to fire, based on the MODIS dataset. The picture on the right is from a detailed study. So the areas in red are human factors, and especially there on the border is saying that it's a high risk, but that are features that I can't capture in this method. Putting the model performance together, we see here the two main areas where North America is very prone risk and Spain is less. When we correct that, Spain becomes more fire prone. I did an area under the curve study here, and the performance of the two models are that North America is more prone. So the studies or the comparison turned out that North America is heavier on fire risk. So that the final conclusion is that more study is needed. So when I'm going to bring this into production, then the areas here highlighted on the screen will be definitely taken into consideration and worked out further. And one of the main points is that the dependency of it's on the screen. I'm rushing this through, so and the presentation is available. I'm take it.
That's a very hot topic for Turkey too, because we have a serious fire problem in Turkey. We lost about 10,000 hectares of forest every year, and I believe it's the same problem in France, in southern Europe,
Yes.
Mediterranean region, and we have seen that the Mongolia has the same similar problems. So if you have any questions, please, you can have it. Yes, please.
Thank you very much for your nice presentation. Nice weather, I think. Thank you very much for your nice presentation. I wonder about topographical wetness index. How did you calculate that, and what are the components of that index?
Let me bring that back.
Yeah. Yeah.
It's on, so we have the flow accumulation is an algorithm that works in this case I use an 8-dimensional algorithm that is calculating how much affected area above the cell you have. So this is based on the slope. So you have the DEM, each cell has a slope deriving to the next cell. And you have the 8 directions, And the steepest one get the highest score, the flattest one gets the lowest score, and from that you can calculate from the top of the hill to the bottom how much accumulation you have, flow accumulation you have for each cell. The slope is then used as a function to give less importance to the flatter slopes. So even if you have high accumulation because you're at the bottom of a valley, because of the slope of that particular cell, you will get a lower score.
Okay. It's a logarithmic value.
Yes.
I think. Yes. Thank you.
No problem.
Okay, another question.
Thank you very much for your nice presentation. I would like to ask you about the fuzzy analysis section in your model. I want to know how did you decide the fuzzy membership functions for the elevation, slope, and aspect?
Where are we?
There can be Gaussian membership function, or all are looks like a linear model. Am I right?
Yes, it is linear, again, because I want to have a generic approach. So within the basins, I just find what is the minimum, what is the maximum, and what is my neutral based on the standard deviation of the different cells.
Okay, I understand that you want to disappear Boolean logic in your model. It's a kind of crisp, you don't want to use crisp values.
No, exactly.
And that's why you prefer linear model, I think.
I tested it with other functions, like a sinusoidal curve, both sides, but it became too complex, and I didn't want the performance increased by making the function more complex than the linear.
Okay, I understand. Thank you very much. And secondly, if you have a time, I can ask, or later I can ask.
Yes, let's ask one more question, and this can be the last one.
Okay,
Please.
and it could be the general approach for me. This question will be the general approach. You have a one estimation model, and can we use this model in Turkey or for the different locations? Can we use this estimation model?
I think you can. That was the aim. So then, can we use this? Can we derive a fire estimate based on global data sets? So it would be very interesting to test. And later in not later this year, but in the beginning of next year, I will do a case study in again in California. We'll compare the model results against an established fire following model. And if you have the data available, I could try to implement it. That's no problem. I think the model should be able to be used in a global setting. So why not Turkey as a case study?
Okay, I see. Thank you very much, and we can maybe speak
Later on the coffee breaks.
Coffee breaks. Yes.
Okay, thanks for the nice presentation again. So we will continue with the next presentation, which is going to be given by Ali İhsan Durmaz. The presentation is about generating DEMs using mobile devices.
Hi, this is Ali İhsan Durmaz. I had a bachelor degree from Yıldız Teknik University from Geomatic Department, and I had a master degree North Carolina State University, Geography and Information Science and Technology Department. Let's look at our view of the presentation first. In this presentation, I will try to create a raster and vector map using a cell phone. Let's start with the outline. In the first half of the presentation, I will talk about the platform of this project developed. In the second part, we will talk about how we can collect point, line, or polygon data from the ground using a cell phone. In the third part, we will compare LiDAR data with GPS data. And in the fourth part, I will show you some examples of elevation models which are created on the cell phone. And in the last part, I will take your questions. I did this project on Nokia 900, and this cell phone was developed by Nokia in 2009. It has 800 MHz processor, 256 MB RAM. The operating system of cell phone is MeeGo. After some cracking issues, you can install Easy Debian on it. After Easy Debian installation, cell phone accepts lots of real computer programs like OpenOffice, GraphGIS, or ArcGIS. All these programs are installed on the cell phone. In my project, I prefer to use Grass because of I mentioned before you, the cell phone's capacity is really very low. It has really very low processor speed, and it has really very low RAM. To collect map elements, first we need to describe what kind of data we need from the ground to draw a map. These are point, lines, and polygons. On Nokia 900, when I checked its developer code, I see that it works with Python, and Python can control cell phone's GPS driver. If you want to create interfaces on the cell phone, you need to use PyQt4 library. It's a Python library, and it allows to design interfaces on the cell phone. This is my cell phone application. I created this one using PyQt library, and this application allows to user collect point, line, or polygon data from the cell phone's GPS driver. On the application, there are two different modes. The first one is normal mode. On the normal mode, user can collect data for each second, and cell phone stores them. The second mode is the average mode. On the average mode, program collects data for a specific time period, and it gets the average.